deeper into the problem. But yeah, I still think that we have some statement for sure.
¿Qué tal? ¿Cómo estás? ¿Está bien, Julio?
¿Tienes conferencias? And then we have to talk about
Está por aquí con José Ignacio, pero hemos preparado todo.
preparation will
Sí, queda. Y ya lo sé, ¿vale?
probably we should write what we are sure think about the local
Okay, so welcome everybody to the joint colloquium between the ICMAT and the University Autónoma of Madrid, the University Carlos III, and the University de Complutense University. So it is my pleasure to introduce the speaker of today, Carlo Gatbarri. He is an expert in arithmetic geometry, and in particular in Diophantine geometry and in the study of rational and integral points and the relationship with complex analysis, with non-Archimedean analysis, with Nevanlina theory, and with transcendental theory. So he is now a professor at the University of Strasbourg, but he was for many years also professor in Tor Vergata in Rome. And he has made research in places like Orsay, where he did his PhD under Spiro, and then in Zurich, in Oxford, in Rennes, in many places. So please, Carlo Gatbarri, that will talk about analogies.
Okay. Of course, thanks a lot. Thanks a lot for the invitation, and particular thanks to Jose. It's a pleasure to be here. And today I will not speak too much about my topic of research, but just tangentially. I would like to speak about some topic which is analogy in science, in philosophy, and why I choose to write it in Greek, because and this will be the only word in Greek, so don't worry. And the point is that analogies is really a tool which is used to understand philosophy, understand science since the Greek philosophy. Aristotle used a lot of analogies, sophism used a lot of analogies, and then even in the Middle Age, analogy was used in theology to speak about God, because you cannot speak directly about God, but you can compare God to other things that we can understand. But this is a topic which will be enough for a lot of talks. And I decided to start to speak about analogy with the definition in the 18th century by Diderot in the Encyclopedia. And here you find is what he writes in French. But don't worry, I will not suppose that you know French. And here is my translation of what the definition of analogy in the Encyclopedia takes a lot more than 2 or 3 pages, and I take something just here. You can find something about this, and what you see, what is interesting to say. They say it means that the relationship or the proportion of that several things have with each other, although moreover different by qualities which are specific to them. So they can be very different, but they share something in common. What is very interesting, in particular in the 18th century philosophy, is what you write after. Reasoning by analogy can be used to explain and clarify certain things, but not to demonstrate them. So it is a tool to understand, not a tool to work with. Nevertheless, you can see that these 2 sentences are essentially in contradiction, in my opinion. So this clarifies already the fact that it's not clear what analogy is. So we just try to understand what it could be, but even when you take somebody who is very rational, like Diderot, write something which is not completely coherent. Anyway, this is why analogy is often seen as the work of intuition in science. So, a precise definition, this I've taken from Encyclopedia Britannica, is the following. So it speaks about analogy between 2 different mathematical topics of physical phenomena when they are governed by similar equations, so that the theory of one is also valid in the theory of other, apart, of course, from the different meanings of the symbol that appears in the descriptive equation. So you have equation or phenomena which formally are the same, but actually describe things which are very different between them. And this can be used to understand one from the other, even if they are very far one from the other. And we will see example in the following. And many scientific people tried to understand analysis, analogy, Poincaré, even Polya, or even Hilbert. And here I would like to quote one scientific who is Oppenheimer. Oppenheimer gave a talk in '55 about analogy in science, which is this one. This is a long talk, but this is the part which I'm interested in. And so now I will use this. Sorry if I cannot do it better. It is very nice because for once I can let Oppenheimer quote himself by himself. So here you will hear his voice.
Metaphor, I can see how I don't even mean similarity, but I mean a special kind of similarity, a similarity constellation between two sets of particulars, two sets of circumstances that are manifestly very different, but have this structural parallel. It has to do with relation and interconnection.
So this is once we can listen to the voice of, I think that in the future it will become easier to listen to the voice of important scientific, but at the moment for me it's, so this doesn't work, to listen to the voice of Oppenheimer is nice, it's interesting. Anyway, I would like now to give some structure. So I would like to describe the general pattern of what I mean by an analogy. So in analogy, we have essentially two theories which are compared, and one is better known, which I call it theory A, and this theory we would like to understand it better. And then we have also another theory, which is theory B, which often is supposed to be known. So we start with something which is known, and we would like to understand something which is less known, and we see something similar, which can be a language which can be speaks about both theory, or a dictionary which can translate the things from one to the other theory, or even some particular feature or some particular feature which between them. And this will be used in many ways. First way, you can translate problem from theory A to problem of theory B. And as you know, as I say, theory B is supposed to be better known, better understood. So probably we can solve this problem in theory B, or see if they are true in theory B. And so have some insight of what happens in theory A. Another way, another thing which can be used in an analogy is you take a theorem, something that you well known in theory B, and try to see if this can be translated in something in theory A, which can be understood, or even often they become conjectures, but sometimes even they become some theory, so some theorem, or some properties that you will understand because of theory B. So theory B tells you what you can discover in theory A. And then another very important thing is that you can also use a method and tools coming from theory B to develop a method and tools which a priori are not evident in theory A, and use to understand better theory A. Of course, this is just a scheme, but this is in the best situation we are in this. We are here, but theory are not so clear when you explicitly work in practical in the true world. Let's see. I would like to start to explain now a very classical example, but probably some of you already know this example, where it, from my point of view, is exactly a way to use analogy. And this is when Euler computed the value of z of 2. And everybody knows it's p square of 6. And now, what Euler really did this, but let's describe. So Euler say, okay, let's pretend that the theory of entire function is essentially the same as the theory of polynomial. Everything you can say about polynomial, you can say it's about integral function. This is not completely false. I mean, they have both interior function and polynomial have Taylor expansion. Then you can find that sum of product of polynomial and polynomial looks very similar, and also they're both closed under derivation. They share many things in common. So let's pretend that they share essentially whatever we want in common. So let's study what happens with polynomial. You take a polynomial and you suppose that they have its roots, which are not 0, and then you can write the polynomial in this way. So this is when you can write in this way, you see that the first coefficient, which is here, is the sum of the reciprocal of all the roots up to a factor, which is A0. So, well, to write this formula, you need to use the fact that the polynomial is of finite degree, otherwise you have a problem. And even better, you suppose that you have a number like b1 minus b1, b2 minus b2, and which are all different from 0, then you can consider this polynomial, which is a polynomial which has roots on these numbers. And this polynomial, you can write it in this way. And so when you develop all the terms of this polynomial, you find again that B1 is the sum of the reciprocal of all the square root, all the squares of all the roots of your polynomial. Of the roots of your polynomial. So the number you physically started with. So you say, okay, this is a particularity of the polynomial, and you say, let's suppose that this works also for entire function. And then, so you say, remark that this is essentially this. So let's work with this function, which is an entire function. And you see that this entire function is like before, as the roots on pi minus pi, 2 pi minus 2 pi, 3 pi minus 3 pi, and so on. But this is not once is infinitely many roots, not many. So you can now write sinus x over x as a polynomial. As a polynomial, I think an entire function, but as a Taylor expansion is like if it was a polynomial, and you can write this formula, which is true. And then you say, okay, let's think that the first coefficient is encoding the sum of the reciprocal of the roots. And what you obtain, that this, you obtain this, which means exactly this. So you obtain that the square, the pi square over 6 is the sum of the reciprocal of the squares of the integral number. Okay, you have to think two things. Most of what I said is true. Everything is true, but most of what I say can be is justified by the classical theory of entire function or infinite product and so on. But when Euler was studying this problem, the theory of holomorphic function wasn't so developed. So he was just using a lot of intuition inside his reasoning, and he knew exactly that this wasn't a true argument. Just say, let's pretend it's true. But he says, it's not a serious argument, but it could be true. And he says, now I can use this analogy to guess the value of z of 2. And you know that when you know the answer of a problem, it's much easier to work with. So he could check, not once he knew the answer, he could check experimentally that it was true, and then he found some other proofs which were rigorous. And by the way, you can imagine, you can say, okay, why don't we try to develop some mathematics around this? You can try, and there is, I think that for entire function it works, but I think that if you work with tangent of x divided by x, it doesn't work. So there is some caveat. You have to be careful on what you are doing. Nevertheless, this is a way to think about a problem using knowledge of another theory. And I think it is very interesting to me. This fact we use analogy is not peculiar to mathematics, as I said, is used also in philosophy, is used in biology, but I have been used a lot also in physics. And I would like to present one example in physics, which itself deserve a lot of work because it is very important in the history of physics, but I am not an expert of physics, so I will just quote it just to show you that analogy is used also in other topics. This is the Maxwell research in electromagnetism. This is a paper, this is a foundational paper in physics by Maxwell, where essentially he understands, I think, the Maxwell equation in physics about electromagnetism, which is called On Physical Lines of Force. Is, as you see, is 1861. And it is very interesting to remark the following. Look what he writes. This is the kind of introduction, and we see another quote from the introduction. In the introduction, say the mathematical laws of attraction, is speaking about electromagnetism, are not analogous to any respect to those of ondulation, while they have remarkable analogy with those of currents, which are electricity, and the conduction of heat, the heat equation, and electricity, an elastic bond. So he sees similarity between different theories, and he uses this similarity, and now see what he says after. This is very interesting. He is the author of this method, so him, of representation, does not attempt to explain the origin of the observed force by the effect due to these strains of an elastic solid, may make use of the mathematical analogies of the two problems to assist the imagination in the study of both. So you see, he knows. He doesn't try to say that electromagnetism and elastic solid are governed by the same thing. He just say, I see that they are similar, so let's study one and try to what we know about the first one to understand the second. And try to develop also mathematics some mathematical tools which try to explain both without trying to understand why it works. So it's a way of thinking. And for him, it was clear he even doesn't hide this. In some way, with respect to Euler probably was thinking that the two things were behaving the same way and there was no problem. Here, this is not, well, this is 60 years after, he's not thinking about this. He say, okay, let's just pretend that we can understand one using the other. So this is a really analogy in the true, more direct sense. Anyway, you could study this paper and try to understand better and better this analogy, but I didn't because I'm not good. I mean, it's difficult. I mean, study physics is already difficult for me, but study the physics of the 19th century is even more difficult. So now I want to speak about a very well-known and very fruitful analogy, which is actual. This is not historical. This is the famous analogy between number field and function field. So you have to see this as the analogy between arithmetics and geometry. So, between arithmetic and geometry. And this starts from something that everybody would teach algebra to undergraduate students, explains to undergraduate students, which is that there is there are three rings which looks very similar, which they have a property which are very similar. One is Z, the word of arithmetic. One is the ring of polynomial, and one is the ring of polynomial of a finite field. And we will see why I put these three examples together, and also please remark the order. There is Z on one side, C of t here, and this is in the middle. It's not by chance. So why? This is what we explain to students. They are principal ideal domain, and also they are Euclidean domain. Okay, you would say, okay, the second implies the first, but doesn't matter. There are two properties which are very similar, and they also have another property which is, so students don't care, but we know it's very important, that if you take prime ideals which are not zero, they are maximal. So they are full dimension 1, and they are regular for people who know commutative algebra. And I would like to remark, because it will be important and used in the following, that here, how they are principal domain. One side you use to compute the sides of the rest, the remaining of the division, you use the absolute value, and the other side you use degree. So just remark absolute value and degree in the dictionary from one to the other are related. And you will see that this will be interesting in the following. There is also another property which is not often explained to students, but which is very important, which says that if you take the field of fractions, so the fraction of this polynomial, and you take the absolute value of this field of fraction, we have that the product of all the absolute value computed in one point, in one element of this field, of these rings, is 1. You have to normalize a little bit to obtain this one. And this is called product formula, which is the base of arithmetics, which is the key point to start many tools in arithmetics. but in arithmetics it's called the product formula. In the geometric, or if you want, over C of t, is this can be, once you translate things in a correct way, is a statement which is very geometrical, which says that a meromorphic function on the Riemann sphere has the same number of poles and zeros, which says that if you want the degree of principal divisor is 0, which is also the beginning of the intersection theory. Of in algebraic geometry. So the beginning of intersection theory is this part. The meromorphic function has as many zeros as pole, and in arithmetics it becomes this. So let's say some other consideration about this analogy. Let's say a little bit more philosophical. Let's say that, as I said before, Z is where you do arithmetics. So this side is arithmetics. On the other side is C of t, is the ring of regular function on the affine line, on the plane, on complex plane, which is the basic object of algebraic geometry. So one side is the basic object of arithmetic, on the other side the basic object of algebraic geometry. And then you have something which is in the middle, which is FQ of t. FQ, sorry, I didn't say, is the field with Q element. Sorry, I forgot to say. FQ of t, it looks a little bit like arithmetic and a little bit like geometry. So one peculiarity of this side is that every quotient field, so every field which is quotient of this ring is a finite field. So this is something which is more in the arithmetic side. And on the other side, these are the ring of regular function of the same, in the actual situation of algebraic geometry of the same object. So this is the affine line a fine line over a field, fine line over FQ, and this is a fine line over C. So essentially the same object for people who study algebraic geometry. And for this reason, André Weil was really enthusiastic, was really somebody who worked a lot of this analogy between number fields and number field, used to say that FQ of t is the bridge between arithmetic and geometry. So when you study this, you are really studying the connection between arithmetic and geometry. And by the way, I would like to quote, but I have no voice, I'm sorry. Again, André Weil, who compared this analogy to the Rosetta Stone. You know, the Rosetta Stone is the stone where there are three languages. There's the same text is written in three languages and have been used to understand hieroglyphs. Okay, and before you complain, it is in English. And here is my translation, and it's trying to describe, this is a famous letter he wrote to his sister, who was Simone Weil, a philosopher. And he tried to describe his work to his sister, and this is part of the letter. And he said, my job involves deciphering a trilingual text, so like in Rosetta Stone. Of each of three columns, I only have rather disjointed fragments, so you know something. I have some knowledge of each of the three languages, but I also know that there are big difference in meaning from one column to the other, and of which nothing warned me in advance. So it doesn't know if something is it works or not. You just see analogy and try to see if the analogy can be translated or not. Over the past few years that I have been working there, I have a bit of dictionary. Sometimes it's on one column that I focus my effort, sometimes on, and I think that this resume not very Italian because we really worked in the three domains with really a lot of really a lot of progress. And but this is not veil. This is not the analogy between number theory and function field is born in some way in the 19th century, and here is it. So this is the theory of function algebraic over one field, I think, and Dedekind and Weber, where Dedekind was a student of Riemann, started to recollect and to publish the paper of Riemann. And then in the same time, they tried to understand and to put order inside the paper of Riemann. And what is very interesting here is that, as I said, I didn't say, but I will say that usually arithmetic is the harder part. We know better geometry than arithmetic. We can do much more things in geometry than what we can do in arithmetic. Arithmetic could be seen also the final step of mathematics. When you understand something in arithmetics, it's well understood, let's say. But what is interesting is that at the beginning of the history, the situation was inversed. You have to imagine that Dedekind was also working he studied the paper, the work of Dirichlet, and then started to develop his theory of Dedekind. The theory of ideal. He invented the word ideal. I don't know if he called it ideal, but surely invented the concept of ideal because they were ideal number. And so he had this very nice theory of ideals of rings, and which he used to understand ring of integers of a number field. And so he said, let's try to use this covering to study covering of Riemann surface of the Riemann sphere. So he takes his theory. I brought this in the theory of algebraic geometry, and using techniques from number theory, algebraic geometry, they could, in this paper, could give the first very rigorous proof of three main theory of the Riemann surface. One is Abel's theorem. The second is the Riemann-Rubitz formula. Please remember this, and Riemann-Roch theorem. They proved that these three theorems, and if you look in the literature, people think that this is one of the most important paper in algebraic geometry, because they really started to use algebraic tools to study analysis, to study Riemann surface. So this is why it is very important. Now I would like to say that this analogy between number field and function field, in my point of view, is essentially the leading theme of part of mathematics in the last 150 years, 160 years. And I would like to give you some example of application of this analogy, but there are just few examples. The one very famous is the one by André Weil, where it studied zeta function of a variety of finite fields, and these were the Weil conjecture, and have been used by Hasse, Weil, Grothendieck used this essentially to develop all this theory of A-type cohomology and even part of schemes have been developed to study this problem. And this was because we started with Hasse. Hasse and Bale wanted to prove a Riemann hypothesis, but they could not do it, so they tried to put the function field case. Another thing which is similar, which is related to this, is that there is a nice parallel between the theory of covering and Galois theory, and this brings the fact that now it's classic and now it's very well understood, but is due to this analogy that the theory of Galois group is the same as the theory of fundamental group. And this essentially has been developed by Grothendieck. By the way, this is the reason why Grothendieck had the Fields medal. And in order to do this, Grothendieck obtained, developed the theory of schemes over DVR, because he proved the comparison between the fundamental group in characteristic P and the fundamental group in characteristic 0. And it was at that time was called Veil conjecture. Veil said that the two had to be the same when you obtain a part, because the parts cooperate to be, and you prove this. Class field theory, which is the theory of abelian extension, which is very old, starts with Hilbert, Harting, Tate, Hasse, and goes on, Veil, and so on, is the theory, and now is completely understood in terms of Adele, which have been, I forgot to mention Chevalet, which have been developed by Chevalet, and is a way to describe the abelian extension either of a function field or a number field, essentially by the same language. There is no difference between the two theory, and they can do. But now people want to be more ambitious, and they would like to generalize class field theory to any kind of extension, not just abelian, so the representation of group and representation of relative group. And this is, there's always probably you heard about the geometric Langlands, arithmetic Langlands, and this is the fact that when you speak about geometric, you are looking to the function field case, and when you look to the arithmetic Langlands, you are looking to the number field case, and you hope. And now Scholz and his collaborator and also Fag, Fontaine, and people like this are now doing a lot of work, at least in the local Langlands, and we hope that in the future it will be also for global. Another thing which really is very related to the analogy between number field and function field is the Arakelov theory. This is Arakelov theory is the analog of intersection theory in geometry. Intersection theory is a very strong generalization of the theorem that says that a polynomial of degree n has n roots, or that two curves of degree d and d prime intersecting d times d prime points, and you can generalize over any variety, obtain a very general theory, and this theory has a parallel in arithmetic, and this parallel starts exactly from that fact that product formula is the same as the number of the fact that the function has as many polars 0 on P1. These two facts put together, and when you translate, you can develop, obtain a theory which needs a lot of work, And here you have the work of Arakelov. You also have Jose, who is a great expert on the test. Faulting, Chile, Sule, and many other people work in this theory, which essentially is motivated by the hope that number field and function field are really the same thing. And there is also something which is, this is unfortunately still very conjectural, which is we hope that the theory of rational point or rational curves, rational point on variety and rational curves on variety and rational point on curves should have a similar theory. And this is called, okay, I forgot to mention Lang. This is called the Lang conjecture, or Faltings and Voita conjectures. They try to explain how to understand, given a variety, you can ask how many rational curves, how many lines are inside this variety, or how many rational points, how many points with in rational coefficients are over this. And we expect that if you know, if you have information about the geometry of variety, so information of the variety of the C, then you can answer to this question. And in some cases known, like the famous Falcon theorem, but unfortunately, there are still a lot of conjecture. There are more conjecture than theorem in this part of mathematics, but the conjecture seems to be strong. We think that we can try to prove this conjecture, not just try to not understand what happened. And there are also other things I will not mention here. There are things related to topology and so on. But there's a but. I would like now I made, I hope, some good publicity to the analogy between number field and function field, and now I would say, but we have to be careful. We have to be careful, and this part is a little bit for, let's say, for algebraic geometers, and we just have to understand the last part of this part, if you don't understand. So, you remember, the first things have been done in the analogy was Riemann-Hurwitz formula. But we will see that, now we will see that Riemann-Hurwitz formula is not completely understood in this analogy. So, I would like to understand, we have to work with logarithmic Riemann-Hurwitz formula, which is a little bit more general. So you have a compact Riemann surface, a divisor, which is a set of points over it, finite set of points over it. And then you have what is called the shift of differential with simple poles around D. And you have the Riemann-Hurwitz formula. Riemann-Hurwitz formula relates essentially the differential with simple logarithmic poles around y to the differential with the logarithmic pole around over x when you have a finite covering, and the formula is this. Then if you pull back the differential with logarithmic poles around d over y, you find the differential of with logarithmic poles around y plus minus some ramification. Ramification keep track of the difference. You have to remark that here I didn't put phi upper star, but I put phi minus 1. It means I just take the pre-image without any multiplicity. This is very important. In the logarithmic differential, the multiplicity disappears. So, okay, so this is either you know or just analytic. And now we apply this to the easiest thing you can imagine. The easiest things you can imagine is you take a function, a rational function, so the quotient of two polynomials, and this gives you a morphism from P1 to P1, which is okay. And then you take this divisor, so the 0, the infinite, and the divisor -1. -1 is to simplify a little bit the formula. And if you take P1, the projective line, and you remove 3 points, you find the easiest hyperbolic algebraic variety. Hyperbolic means something which is uniformized by a disk. So the easiest, okay. P1 minus 3 points is one the easiest things. All others are more complicated. So we apply the situation into this. We apply the Riemann orbits to this situation. One thing we obtain is that if you consider this divisor and you take the pullback, you obtain the maximum of, this is just a computation, the maximum of degree of f of p and g of p. And then when you take the set theoretical preimage of these three divisor, so you can see here is set theoretical means the point such that the image g goes to 0. So the point where the prime factor of g, the prime factor of f is this, and this is the prime factor of f plus g. Plus is minus, so tend to be a plus here. And then you get this theorem. This theorem is just you just forget ramification. Just forget ramification, and you put using Riemann-Hurwitz formula, and you compare the differential with logarithmic with the logarithmic poles, and you forget, really don't care about ramification. So here you obtain an inequality, and so remark that you observe that here you have polynomial which may have roots with very high multiplicity, but on this side there is no multiplicity. It's just the number of divisor, number of prime factor of these three polynomials. So this is the non-triviality of the theorem. One side is there can be a lot of multiplicity, the other side no. And now, okay, let's say now we use our translation from number theory, from function field from geometry to arithmetic, and remember what the degree was, as I told you before, was the absolute value. And you even do it in a very weak form. So you don't want exactly this formula, but something which is weaker to this in this context. So you put some epsilon which should be there, and then you fix an epsilon, and then you suppose this is the analog of what should be the analog of what is written there exists a constant for which the following holds. You take two prime number a, b runs in Z, and we call a plus b equal to c, like there, f, g, f plus g, and you find the following inequality. The following inequality should be the analog of the inequality above. If you really want similarity, you should put a log to obtain that sum becomes product becomes sum, and this should be the direct translation of the theorem above, which is the famous ABC conjecture. So what is a bit weird is 150 years ago, they started the analogy and they proved inside the analogy Riemann-Hurwitz, but Riemann-Hurwitz is still not understood inside the inside this analogy. So we could do a lot of things, but Riemann-Hurwitz remained there as a problem to understand. So is it true? Is it false? Is it breaking the analogy? I don't know. I just say that it is there. By the way, there's no epsilon there, and there's an epsilon here, and if you put epsilon equal to 0, there is a contour example. So the direct translation is false, but we can adjust the translation to keep it perhaps. And I don't want to speak about the situation of ABC conjecture because it takes a lot of time. Okay, perhaps between you are thinking, somebody of you are thinking, but why you are speaking about this problem of analogy? To understand analogy, analogy already exists and is encoded in mathematics, and this is called equivalence of categories. When you have equivalence of categories, you can say two things are the same. I can translate the theorem from one side to the other, and this is also used by Bourbaki when they speak about transfer of structure. They try to make some general statement and then they apply to different theory. And they say, okay. This should be the same. But about this, I would like to quote again Bailey, because this is a very, very nice statement, quote of Bailey, which is now it's in French, now it becomes in English, and it's very nice, I think. So it says nothing is more faithful, all mathematicians know it, than these obscure analogies, this vague reflection from one theory to another, this fugitive caresse, this inexplicable confusion. Nothing gives more pleasure to the seeker. A day comes where the illusion dissipates, presentiment changes in certainty. Twin theory reveal their common source before disappearing. As Gita, I cannot put, teach, we attain knowledge and indifference at the same time. Metaphysics have become mathematical, ready to form the material for a treatise whose cold beauty can no longer excite us. So it's almost a polemics against Bourbaki for me. But and then we conclude with a nice remark. Fortunately for researcher, as the fog dissipates on one point, it's only to reform on another. So in some way, it seems that Weil, and I agree with him, he says that this analogy is a way of thinking, a way of using intuition, a way of working. When it's clarified, it's not more interesting. It's the fact that we see things which are far from one from the other that is fascinating, not the fact that they are near and so on. And I think I will stop here.
Thank you very much for this talk. Are there questions or comments?
Okay. So about this analogy between number fields and function fields. So on the left-hand side, well, you have two kinds of function fields, actually, right?
Mm-hmm.
But anyway, on the left-hand side, you have these non-Euclidean absolute values, which I guess correspond to valuation of points or something. But you also have a Euclidean absolute value. Is there any analogy on the right hand side?
I don't know. This is one of the things that we try to understand, and there are some, let's say, we don't know. This is the answer. The answer. We would like to understand this, but there is also, even in the recent work of Scholze and all the other mathematicians, even Manning, was trying to work in another direction, try to see if Euclidean, so in periodic case, you have a natural ball, which is integers, which is a compact set inside, which is you can, which is attached to the equation, ZP, which is a geometrical object. It's not just like Z inside Q, which is, from the point of view of analysis, has no rule. And so people try to see if you can do the same in the complex case. So to find a way to attach to a variety a sort of model or lifting somewhere. So it is not the answer to your question, but it's the answer to the fact we know the problem and we try to attack it in a different way, because at the moment we have no idea. It could be, or perhaps, I don't know, stone, this Gelfand stone theorem, which says that given a variety and the algebra of continuous function, given a compact variety and the algebra of continuous function, this is essentially an equivalence of category, and so perhaps this could be a way to attach to a variety something which looks like periodic. But let's say we try. Perhaps the idea is to try to not to see Archimedean places as if they were non-Archimedean, instead of if they were as the others, let's say. But we don't know.
More questions?
Can I ask a rather technical question, but not hard? On the analogy giving rise to the ABC problem?
Yes.
Could you please show your slide? It's better, it's satisfying.
Yeah.
Yes.
Okay.
No, that's perfect. So in the original thing with the polynomials, right-hand side, you have the degree of f, the degree of g, and no mention to the degree of f plus g because it's smaller. So there is no need.
Yeah.
However, in the ABC conjecture, generically, somehow if A and B have the same sign, the max will be the norm of C.
Exactly.
So, I mean, I know this is an analogy, I just remember what it is, but to me, this looks like a big difference.
I agree with you, and the point is that you remember that in the proof we worked with a meromorphic function. And then we obtain a theorem about the meromorphic function. Here, these are entire functions, let's say. So this perhaps is the way. And there is also this fact that in over Z there is n, and n. Okay, there is an orientation inside Z, and so I agree with you. If you keep track of the orientation, you could see here. Otherwise, you don't. Is it due to the fact that when you take the sum, the degree can decrease, or I don't know? But it's true that there are many things should be clarified. Many things. I agree with you, but as I say, it's an analogy, so it's just a way of thinking. Perhaps this is completely false. I mean, it's just here because we like to hope to the analogy, but there's no reason why this should be true. Up to the fact that we are not able to disprove it.
So more questions?
Actually, the statement of this theorem,
Mhm.
which I never seen before, reminds me of Bailey's theorem of Grothendieck's theory of the Soldan fund. You ever heard about that?
Sorry?
Bailey's theorem.
Yeah.
Grothendieck's theory of the Soldan fund. It sounds a little bit as it could have to do with something, you know.
It has to do it. Alors, in this form, I don't know, perhaps you can find in with a different proof, much more complicated. It's proved in the book of algebra of Lang. You can find more or less in this form. But it doesn't speak about Hurwitz's formula, so it makes an explicit computation and becomes very difficult to understand what it is. It looks magic in this statement. And I think that in this way it looks very natural. But it is very strictly related to what you say, because if you know that there is also another problem in arithmetic, which is called effective Mordell. Effective Mordell means given a curve you want to give of genus bigger or equal than 2, you know that there are finitely many rational points, and you want to find them. And if you apply this plus Bailey, you obtain a theorem of Elkis, which says that you can do it. And okay, so there is also another thing that if you have a very strong way to find rational point of curve on any curve, you apply Bailey again, and you find this. So this seems to be related to this.
Any other question? So if not, let's thank Carlo again for his talk.